So here we're going to explore some relationships between areas and volumes and look at a thing called the scalar triple product. So I'm going to take for granted here that the magnitude of u cross v is equal to the magnitude of u times the magnitude of v times the sine of the angle between them, theta. Okay, so looking at that picture, here's a vector v, here's a vector u, here's an angle between them, theta, right? And I'm looking at this parallelogram here. Okay, now I'm going to throw a quick altitude in here. So I'm going to look at this height here. I'm going to call that h. Actually, you know what the heck? Let's call that thing a. So I'm looking at a and I'm thinking, all right, if this were just a parallelogram, right? The area of this parallelogram, so right, if this just was a side length, would be given by whatever the number a is times the length of that side. So it'd be a times the magnitude of u. And then I'd be like, okay, well, what the heck is a? Well, I've got a little triangle there, right? So I can pull that little triangle out and I can think this way. So I've got an a here. I've made that altitude, so that's a perpendicular there. I don't really know how long this is, but I know this side is magnitude of v long, right? I know this angle in here is theta. So I can say, all right, the opposite over the hypotenuse ought to be the sine of theta, right? So a over the magnitude of v ought to be sine of theta. So a is mag v sine theta. Great. I can just toss that in here, and I can get that this is the magnitude of v sine of theta, and then u. Okay, cool. This gives me a double check on a fact that I claimed earlier, which is that this number, right, the magnitude of u times the magnitude of v times the sine of theta, is in fact the area of the parallelogram. Cool, great, awesome. All right, so now we're going to look at this thing called the scalar triple product. And this thing's a little bit hard to hold on to. So I'm going to draw a picture. I'm going to do my level best here with the drawing pad. It may be a little shit. My apologies on the shitness of my drawing. So here I've got a vector u. Here I've got a vector v. That vector v is also back here. I've got another copy of my vector u here. Right, so I've got that vector u in the background. I'm going to not label those because this picture is going to get confusing enough here in a second. I'm going to draw a vector up here. That's going to be w. Right? And then I've got a box to fill out. So I'm going to fill out my little box here. So that side's going to be solid. Oops, that side should have been solid as well. Okay, so that's a copy of the vector u lifted up there. This is a copy of the vector w over here. Oops, that's a crummy line, Joe. Here I've got another copy of my vector w. Here I've got a copy of my vector v. Here I've got a copy of the vector v. In the back here, there's another copy of w. And then across this back edge, there's another copy of u. Okay, so I've got this whole shape here. Now, I'm going to draw a line that's going to be a bit like my altitude, right? So that's going to be a vector that starts down here and goes directly up to this corner, and that vector is perpendicular to the plane that it's sitting in, right? I'm going to call that vector h for height. Okay, so here's a couple of things I know. I know that the area of the base here is equal to the magnitude of u crossed v. I also know that's the area of the top, right? This thing is called a parallelepiped. It's like a box that's tipped over a little bit. If you want to make one of these, take a deck of cards and then just kind of push on one of the corners so you get a tipped box. Okay, so I've got my area of the base, and then in order to figure out the volume of this shape, right? I'd take the area of the base, the magnitude of u crossed v, and I'd multiply by the height. So in my case, that's going to be the magnitude of this h vector, right? Okay, so where am I going to get the h vector's magnitude from? Well, that's actually going to be something I can lay my hands on astonishingly, right? So I'm going to think to myself, all right, I need to think to myself. I need to think, well, what do I know about h? Well, I know h is perpendicular, right? So I think that h is actually parallel to u crossed v. And in fact, I think that if I moved h over here, right, if I thought to myself, all right, here's that vector u crossed v someplace out here, right? That's the vector u cross v there. I think if I simply slid h over, I would notice that that's w projected onto u cross v. So I think that h is in fact, h is in fact w parallel, and it's parallel to u crossed v, right? It's the piece of w that's parallel to the vector u cross v. And I have a formula for that, right? So where am I going to get a formula for that? Hell, I don't know. I had it in the projections section. So maybe I'll just go up to the projections section here and grab a formula for W parallel, right? So I'm just going to copy this thing and bring it back down here to my scalar triple product land. I'm just going to drop it up here, and we'll just turn this pen color like orange or something so that we don't think it's something we've just done. Okay, now this was W parallel to a vector V, so I'm going to have to make a quick substitution here, right? Because I am looking for W that's parallel, but I'm looking for it to be parallel to U crossed V. So I'm just going to rewrite this in blue. So this is going to be H is going to be U crossed V times this scalar. And this scalar is going to be U crossed V dotted with W. You need to see that. Nothing interesting, but. And then on the bottom, I've got U crossed V dotted with U crossed V. So there's going to be some simplification I can do here. And I'm also looking for the magnitude. Most of this crap is going to be a scalar, right? This is a scalar on top, that's a dot product. This is a scalar on the bottom, that's a dot product. So here, I'm going to have a single vector scaled. So when I take the magnitude of a scaled vector, I'm going to get the absolute value of this scalar times the magnitude of that vector, right? So I'm going to have here the magnitude of h is going to become the magnitude of u crossed v, that's this guy here, times the absolute value of this scalar. So that's going to be the absolute value of u cross v dotted with w over, and on the bottom I already have a magnitude squared. So that's going to be the magnitude of u crossed v squared, because that's just what I get when I dot product a vector with itself. Then you might notice, oh, hey, look. This magnitude squared and both of these guys cancel out. I know that went kind of fast, so I'm just going to do a little bit of drawing here. So this piece here is that guy there. And all of this stuff came from this magnitude of h here. Okay, after we do our cancellation, we find out that our volume is actually just equal to the absolute value of u crossed v dotted with w. And I'm just going to rewrite this real quick. And the way I'm going to rewrite this is I'm going to rewrite this as it's the the absolute value of w dotted with u crossed v. This is just a cosmetic rewrite, but it's going to make my life just a tiny bit easier because I've actually seen this somewhere. So this somewhere that I've seen this, right, is I know what U cross V is, right? The way I'm going to get U cross V is I'm going to go like this. I'm going to go U cross V. Actually, you know what? Let's just go grab it. So I already have the cross product here. Here's the formula for getting U cross V, right? All right, so I'm going to just take that formula. This is mostly to save you watching me write. I'm just going to drop it in here, right? So this is just our same formula for U cross V. We write everything into the second and third rows of a determinant. We put a symbolic ijk in there. We crank on this thing. We get this number or this vector. Okay, now I'm going to take that and I'm going to dot product that with a vector w. So when I dot product w with u crossed v, right, I need to multiply the components of w by the components of u cross v and then add up the kind of results, right? So I'm going to get the determinant of u2, u3, v2, v3, that's the I component, times the I component of w, right? Minus u1, u3, v1, v3, times the w component in the second spot, so that's w2, plus this determinant of u1, u2, v1, v2 times that third component. And I'm just adding these up. But that's the exact same thing I would have gotten by taking the determinant, well, really the absolute value, right? So I'm doing absolute value of this thing, should be the absolute value of this thing, should be the absolute value of the determinant of a matrix that's W across the first row, U on the second, and V on the third. That's kind of freaking cool, right? So there's this relationship between determinants and volumes. There's a relationship between determinants and area. Part of that is that you can think of the determinant as an area distortion factor. So if you apply the matrix A to the three-dimensional unit cube, right, the determinant of that application is just the parallelepiped where the sides are given by the columns of A. And so what I get is this like universal factor, right? A matrix stretches things into bigger or smaller volumes, and the rate at which it does that, right? The multiplication factor, essentially, like if I take a box B that has a volume and I push it forward using a matrix A, that new box B prime has a volume that's equal to the old box's volume times the determinant of the matrix. That's a very cool thing. It gives me a good reason to know that a singular matrix should have a determinant of 0, right? If I'm losing information by smashing a dimension, I'm decreasing to 0 the volume of a box. This is very cool, actually. So that's that kind of relationship here. This thing where you take the W dotted with U cross V, that's the scalar triple product. It happens to be the same thing as taking the determinant where you put W, U, and V in the rows. You can calculate it either way. It's a very cool quantity. It's a neat relationship. I hope you get a kick out of this as much as I do.